All right, with this lesson, we're going to be moving into our fourth unit on probability. Probability is something that I think most people are aware about. You hear all kinds of probability statements being made on any given day. You hear the probability that it's going to rain. You hear the probability that a sports team is going to win. You hear all kinds of probabilities in the daily life. And I think intuitively, we all have a pretty good idea of what probability means. Now, just to be clear, most of the probability that we're going to cover in this course is going to be theoretical probability. Today, we're going to talk a little bit about experimental probability. Now, the good news is the calculations are exactly the same. It's just how you collect your information is a little bit different. So getting into what we're mostly going to do, not today, but pretty much for the rest of the course, is that we're going to do situations where we assume that outcomes are equally likely. So some examples there, if you flip a coin, it is equally likely that you're going to get a head or a tail. Now, on any given flip, you have no idea which one you're going to get, but if you repeated the experiment a bajillion times, you'd expect to get heads half the time and tails half the time, give or take a little itty bitty bit of difference. Similarly, if you roll a die, each outcome is equally likely. That doesn't mean that you're going to get one of each number if you roll the dice 6 times. It just means that each number has an equal probability of appearing. And likewise, if we're dealing with a deck of cards, the probability of drawing any single card is 1 in 52, if we're assuming a 52 card deck with no jokers, which in this course we always will. Okay, so that aside, experimental probability, a little bit different. Good news, as I said though, calculating is exactly the same. Regardless of what we want to do, the notation is the same, the calculation is the same. The probability that something will happen. So I'm just going to zoom in for a brief moment, or try to zoom in and have no luck whatsoever. There we go. The probability that A will happen is equal to the number of ways that A can happen divided by the number of ways anything can happen. And if this looks familiar, you might remember back from Unit 3 when we talked about set theory. A can be considered a set, so that's the thing that we're looking at happening. And S is the universal set, which is all possible things. Let me just get that back so we can fit it properly again. There we go. So again, if we think about what we were just talking about, flipping a coin and getting a head, there would be one way to get ahead and two possible outcomes. That would be 1 out of 2. And then we normally convert that to, we get it as a fraction automatically. We can convert that to a decimal or a percent. Percent would be the preferred method in this course. Same idea. If I roll a die and I want to know what the probability of rolling a 5 is, one way of getting a 5, 6 ways of getting a number when you roll a die, so 1 out of 6. And the number of ways I could get, for instance, the ace of spades in a deck of cards would be one way out of the number of ways that I could get anything, which is 52 ways. Or I could do the number of ways of getting any ace out of the total number of cards in the set, which would be 4 out of 52, or about 1 in 13. Actually, exactly 1 in 13. Now, this next part probably goes without saying, at least I really hope it does. But probabilities, if we're giving them as a number, a decimal number, will always be between 0 and 1, or as a percentage between 0% and 100%. You can never get a negative probability of something happening, and you will never get a probability greater than 100% of happening. I should point out that a lot of people get confused with when you're allowed to have numbers greater than 100% and less than, up to 100%. So for instance, if I expected to make $100 today shoveling snow, but I went out and made $120, I made 120% of what I thought I could. That's fine to have a number over 100% because I got more than I was expecting. When it comes to probabilities, though, you can never have more than 100% because there's never more than a certain exact value that you'll like if once it's 100%, you're getting that value no matter what. So if I draw a card from a deck of cards and I want to know what the probability is I get a card, obviously I can never do better than 100%. Also, if we think about sets, since A is within the universal set S, It's impossible to get A with more elements than S has. S is the universal set. It's everything that we could possibly consider within the question. And it's impossible to get more things than there are in the universal set. Okay, back to the idea of experimental probability and theoretical probability. Theoretical probability is making the assumption that all outcomes are equally likely. So we're going to do that, like as I said, through most of the course with things like flipping coins, rolling die, and drawing cards from decks. Experimental probability is something that we actually have to do an experiment to figure out. Now, the interesting thing is we can do something that could be theoretically solved experimentally, and we're actually going to do that very shortly. But then there are things that are experimental that you have absolutely no way of doing theoretically. So for instance, if I said we're going to flip 10 coins, what's the probability of getting 5 heads and 5 tails? That one is something we could do theoretically, but we could also do it experimentally. If I said, what's the probability of someone on my street, a random person on my street, owning a cat? Um, I don't know how I do that one theoretically, because all outcomes are not equally likely. I can't just say, well, you can have a cat or not have a cat. That's one out of two options. So there's a 50% chance of everyone having a cat. That's obviously not true. Because if that was true, then there'd also be a 50% chance of anyone owning an elephant, because there's one way to own an elephant and you can have one or not have one. That's two ways, 50%. Um, experimental probability you actually have to do. So a good example of that is racing. And we already talked a little bit about horse races in an example a while back, and that was a little bit fictitious when we talked about, what are the probability of winning? Because we kind of mentioned that, even though it wasn't part of the official lesson, because that assumes that every horse in the race has an equal probability of winning the race, which we know is not true. Some horses are faster than others. There's likely a horse or two in that race that stands absolutely no chance. I'll tell you right now, if we got together as a class and I ran a race with you guys, um, there'd be like 30 of you and one of me. So that means that any one of us should theoretically have a 1 in 31 chance of winning, but I do not. You are all going to beat me. The only chance that I have of winning a race against any of you is if literally all 30 of you fall down and multiple times and never get up again. Like that's the only way I'm going to win a race. I am slow as anyway. It doesn't matter. But that's something that we would do experimentally and not theoretically. So if I wanted to figure out what the probability of someone on my street having a cat is, then the only way that I could do that was basically go around to the people on my street and say, okay, hey, there's 35 people on my street, and I asked, and 6 of them have cats. So the probability of any one person having a cat, if they're chosen at random, is 6 out of 35, which is about 17.1%. Okay, so the calculations for this are super simple. So that's why I'm not actually pulling up my marker and pen today to write anything on here, because I don't think I need to. Um, what I am going to do though is run you through a little experiment that I actually do with my in-class students when we can actually like sit there and play. And that's actually part of the reason this lesson is short, is because the rest of the class is usually taken up doing this little experiment. So the experiment that we do in the class is that I give every student or pair of students 10 coins. They get pennies, not loonies, but I can put any coin I want on here, so I chose loonies. And what they do is they take these 10 coins and they flip them and they count how many times they got heads and how many times they got tails. Now in this case, head is always the picture of the person. So in this case, the queen. And the tail is always the other side, regardless of whether or not it's an animal with a head or not. So in this case, the loonies are the tails. And the reason that we did this is we wanted to run a trial. We wanted to see if we could theoretically, well, sorry, not theoretically, if we could experimentally figure out what the probability would be, and this is the actual thing we did, the probability that you pass a 10 question 10 question true or false quiz by randomly guessing. So the idea here is that if I get ahead, I'm going to consider that I got the question correct. And if I got a tail, I'm going to consider that getting the question wrong. And I'm going to do 10 coins because we said there are 10 questions on the quiz. So the goal is to get at least 5 heads so that we pass. And if I look on the screen here and I count up the number of heads and tails, I get 5 and 5. That's a pass. If each of these represents one question, I got 5 questions right, 5 questions wrong. And I can flip these again and get different results. So when I do that, this time I got 1, 2, 3, 4, 5, 6, 7, 8. I got 8 questions correct and 2 questions wrong. And here I only got 2 questions correct and 8 questions wrong. Now I do want to point out that these random things I'm doing, I'm not premeditatedly coming up with answers. I'm just clicking the buttons on the screen. I have no idea what the outcome of um, any given trial will be, but I can make some guesses based on my personal understanding of theoretical probability that we're not quite ready to get to yet. But I'm going to make predictions. So you'll notice that my tab here does have one more little thing there. There's a tab there. It says D grades, and it lists a whole bunch there. I'm just going to keep that in mind. I'm going to ask you right now to guesstimate in your head, or write it down, or yell it to, I don't know, someone who's near you at your computer. But I want you to estimate what you think the percentage is that, or probability is, that you'll pass a quiz with 10 questions, true, false, if you randomly guess on every quiz or every question. So I want you to just think about how you would do that, what probability that would be. Do you think it's going to be a high probability, a low probability, about 50%? I want you to actually come up with a percent number, and I want you to write it down or at least remember it. And then once you're done that, we're going to basically do this experiment again, except instead of flipping coins 10 at a time, which is time consuming, and it also takes time to write them down. We got 1, 2, 3, 4, 5, 6. So that was 6 out of 10. This one is 1, 2, 3, 4, 5 out of 10. Okay, this would take a long time to do a whole bunch of trials. So what I've done is actually set up something a little bit different. Now, I'm using Microsoft Excel. This can be done using Google Sheets, but since you don't have to reproduce it, I'm going to use Excel because it's nicer for this, and I'm more familiar with how to use it. So here's what I've done. I've said, okay, these columns are going to represent the 10 coins that we're going to flip. And then I'm doing 10 trials. We just have to do one trial and then repeat it over and over again. So I was doing one trial at a time. But this first trial, I have 10 coin flips. Ones represent heads, or in this case, if I'm thinking about the quiz, ones represent questions I got right. Zeros represent questions I got wrong. And I just use this function up here, equals rand between 0, 1. So it's just going to give me a random whole number between 0 and 1. And I just messed up the sheet, so let me undo that. Controls. Oh, maybe I didn't mess it up. Okay, we're good. Okay, so I have a bunch of random numbers, zeros and ones. And then what I have down here under total is the number of questions I got correct. So I just added up all the numbers in each row and said for trial 1, I got 6 out of 10 correct. For trial 2, I got 3 out of 10, and so on. And then beside that, I did a little if statement, and I basically said if it's greater than 5, keeping in mind that, or sorry, if it's greater than 4, keeping in mind that these are discrete values, so there is no such thing as getting 4.3 out of 10. This is basically saying if I get 5 or higher out of 10, I'm going to pass. So if I get 5 or more out of 10, it just gives a 1, so I passed, and if it doesn't, it gives me a 0, and that's a fail. And then what I've done over at the side here is said, how many trials did I do? And what is the number of passes that I got? And then the pass rate. And that red number, that 60%, is representing that I passed 60% of my trials. Now, I only did it 10 times, which is not a lot. And if you think about it, if I'm guessing, let's say that the correct answer to this is that I passed 38% of the time. Well, if it is, there's no way I'm ever going to get 38 with 10 trials, because each trial represents 10% of the outcomes. So I'm only going to get something that's a nice multiple of 10. So it's impossible to get the right percentage with only 10 trials. It's kind of like determining the percentage of getting heads or tails on one flip if I only flip once. If I only flip once, I'm either getting 100% heads or 0% heads. So now turns out that if I click on the screen pretty much anywhere, just kind of double click, it will recalculate all these random numbers for me, and then it'll give me a new pass rate. So these 10 trials gave me a 60% pass rate. Oh, those 10 trials, oh, sorry, it just took a second to update there. Those 10 trials was a 70% pass rate. Another 70% pass rate. We'll do it one more time. And this time it was a 50% pass rate. So it looks like we're passing a little bit more often than we're not passing. That's interesting. I know most students usually guess 50% of the time you'll pass the quiz and 50% of the time you'll fail. It seems to be a little bit higher than that, but again, this is a small number of trials. So what I'm going to do is I'm just going to switch over to what looks like the same thing, but instead of doing 10 trials, I've now set this up to do 100 trials. And I'm just going to randomly generate again so that you don't think I'm just stealing the number or programmed the number in ahead of time. And if I do 100 trials, this says I passed 58% of the time. So 58% of the 100 trials for 58 of the 100 trials passed. And if I do it again, I get 66% of them passed. I'll do this just a couple more times so you can see it's generating random numbers. 54% passed, and the last one, 63% passed. Now, if you're wondering why it's kind of taking a little while for it to calculate, it actually isn't because of the numbers here. It's because of the numbers in the next few, because it actually generates them for all pages within the spreadsheet. And now I'm going to go over, instead of doing 100 trials, I'm going to do 1,000 trials. So 1,000 trials, I'll just get it to regenerate. And it says it passes 62.3% of the time. And if I do it again, 62.6% of the time. And 63.1%. 61.2%. So it looks like we're getting mostly numbers in the low 60s. 63.1, 63.4, 60.4. Okay, I think we're probably good. So 1,000 trials, we're starting to get a little bit more consistent. Our numbers are bouncing around within a few percent of each other, but they're pretty much in the very high 50s or low to mid 60s. Let's do 100,000 trials. Now, I'll tell you, this took me a while just to scroll down that far to cut and paste that many. And this is the one that's actually creating the lag that's taking so long for it to recalculate each time. But if I redo this one, okay, 62.3%. Do it again, 62.104. 62.4, 62.3, 62.7 almost, 62.2, 62.1, 62.6, 62.3. Okay, so I think what you're seeing is that a lot of these numbers seem to be in the 62 point something range. I can't recall if there was one that was 61 point something, but or possibly 63 point something, but mostly in the 62 range. Okay, so I could do this with more, but I think you can again imagine that if I go up to 1,000,000 trials, keeping in mind that 100,000 trials with 10 flips each is already 1,000,000 coin flips, I don't want to make the computer die on me or take too long to recalculate these. So I think I'm going to stop at 100,000 trials. And they seem to be numbers that are pretty close to 62 point something. And I'm going to reveal a little secret now. I'm going to go back to my web page. And you remember over here, for an unknown reason, I put down D grades. These are the grades that you would get if, or basically these are all the grades that would result in a D. And I already clicked on one just to give you something here. And the number is actually my prediction. My prediction was 62.3%. would be a passing grade. And by prediction, I mean that I understand the rest of the lessons in this unit already, and I calculated it. And we'll see later how to calculate this percentage as a theoretical value. But the theoretical value we should get is 62.3. That's rounded slightly, but it's pretty close to exactly 62.3. Um, and we can see that when we do this experimentally, we are getting numbers with 100,000 trials that are extremely close to 62.3. We're never going to get it, well, we may get it exact. I think we actually did get 62.3 exactly twice. But we're going to get numbers around 62.3 because any given time that we do this is going to be some fluctuation around numbers. We're never going to get exactly, and if we do, it's kind of a coincidence. But again, just a few more times, and you'll see that we're getting numbers pretty close to 62.3, give or take about 0.2 or 0.3%, which isn't too bad. 62.4, 62.2, 62.4, 62.2, 62.2, 62 point, almost 62.3. It actually rounds up. But we're getting numbers that are extremely close. So a couple things I want you to take away from this are, first of all, when you do a small number of trials, you might get somewhat close to the correct answer, but you haven't done enough trials to really get any real consistency and have a good idea. The more trials you do, the more likely your percentage or your probability is going to be to the correct answer, whatever that is. Now, one more thing I want to do just before we go to foreshadow just a little wee bit something that's coming up and to pull back something that we did earlier in the course. I'm going to take basically what we did here, and instead of just saying whether we passed or failed, I'm going to count up the number of times we got 0 out of 10 on the quiz, 1 out of 10 on the quiz, 2 out of 10 on the quiz, and 10 out of 10 on the quiz. Now, this is with the 100 trials. So what this is basically a bar graph of is the number of times that I got 2 out of 10 on the quiz. So basically 2 coin flips, 2 heads out of 10, or in this case, 2 ones out of 10 random number generations. And what you'll see is that it looks like there's a lot in the middle and less towards the ends. So we get 5s quite often. We get 5 out of 10 quite often, but we get 0 out of 10 and 10 out of 10 very infrequently. In fact, in this particular set of 10 trials, 100 trials, we never got a 0, a 1, or a 10 out of 10. We did get 1 9, I think. Yeah, just 1 9. Okay, and same as I did last time, I'm going to just randomly regenerate these numbers here. By the way, the numbers that we did, they're all over here. I'm just moving over to focus on this graph. So you're going to see that as I regenerate this distribution shape is going to change. Again, random every time. But I think if you look at most of them, they should look like a familiar shape back from maybe Unit 1. These are all a little different, but they all have a similar overall shape, which is a peak on the middle, in the middle, and then they're kind of, or near the middle. Again, this is only 100 numbers, so or 100 trials, so that's not a lot. But we're seeing that for most of these, we kind of have a fair bit of central data and then very little data in the upper and lower ends. You guys remember what this kind of distribution is called? This looks a lot like a normal distribution. It technically isn't because it's discrete data. Normal distributions only apply to continuous data, but it does have that same shape, that bell shape. It goes up in the middle and down on the sides. Now, what do you think is going to happen to this shape as I increase the number of trials? Here with only 100 trials, we get a fair bit of randomness in the shape of this graph. As we keep recalculating, it keeps changing shape, despite the fact that most of them are similar, peak in the middle-ish, and then drops down at the ends. But I bet you if we did more trials, this would be more consistent. So I'm going to go back to 100,000 trials. Look at that graph. Does that not look like a normal distribution to you? extremely little data at the beginning and the end, lots of data in the middle, and I'm going to recalculate it a few times, and I want you to just focus on the actual shape of the graph and see how little it changes with 100,000 trials. Okay, if you look closely, there were a couple things that moved there, but not very much. Yeah, these are pretty minimal moves. So it turns out that when you've got this many trials, you get something that is very close to a normal distribution. This is actually a different type of distribution, one that works for discrete numbers. It's called a binomial distribution that we're going to get to, I think, in lesson 3. And it is, I would say, the most fundamental idea in this unit. And I will say that we are also going to take a look at approximating normal distributions with, um, approximating binomial distributions with normal distributions because their shapes are so similar and so consistent. And what you'll see is that it does let us solve some um, larger questions much quicker by using a normal approximation. All right, I'm going to stop there. Experimental probability, pretty straightforward. Try some of the homework questions, and what you'll see is that it really is just the number of ways you can get what you're looking for divided by the number of things you can choose from. If you get that one basic little equation, you should be good to go. So I will let you go do that, and I will see you in our next lesson on theoretical probability. Later.